It's live again. We are going live.
Mirror is working. It's always mirror, yeah. So
Huh?
this you can have like a control screen, but it's mirror going to work.
Then I should watch from my phone and then like control the panning. Can't see.
Let's just slowly way down.
Oh shit, I don't have the Facebook application.
I think it's, you have to, maybe you should let you have like play stuff. It's not control L should work.
Yes.
Yeah. And this one, and the clicker was going to work or not? Oh, so maybe we can try the clicker.
I need to download the application to watch it live.
Yeah. Sure.
I need the Facebook application to watch the video live. Okay, fix it.
Do you?
Yeah, I need to Skype.
I will get some people.
Oh, I think it's not working.
Oh, what happened?
Okay.
I want to charge. I want to charge my laptop.
But why do you need the paper?
Huh?
Oh, you need the paper.
You don't know?
Right again.
Actually,
It's the heck, yeah.
Indonesian teachers.
Oh, wait a moment. I have to put it on. Oh. It works. So that's it. Perfect.
Oh, Joaquín,
This is like the oldest button.
is it alright?
Yeah, this is me. I have to put it like this. I have like a little good light on my face.
It's just
I think it's okay. It's pretty good.
It's live.
Yeah, I'm like this. I can see. Oh, it's live.
Yeah.
Well, which you are
NUS Hackers group.
in what?
The NUS Hackers Facebook group.
Oh, okay. But it's like in Twitch or something. But what is that?
Yeah, it's similar, I guess, on Facebook.
On Facebook Live.
Yeah.
Okay, Facebook Live. Yeah, so I'm live. Hello, everybody on the internet. 1 million people. I mean, scaling to millions. I mean, there must be 1 million people there watching the So, okay, so this is like, actually I changed the slide. This is, I was in academia. I mean, I'm not teaching at the university, but I'm with PhD students and doing research. I was in the academia like a few months ago. And now I'm an entrepreneur first, that is a kind of accelerator to make startup. And now I'm building a startup with exaQuark that is based on this technology. So we use this technology. This is like an algorithm, but I mean it's coded. So now let's say it's a technology. So what is about? Hang on. Yeah, okay. And what it's about is about the scalability of virtual world. What is the problem of the virtual worlds? That they have that. Okay, that's so cool. And so what's the problem? Is that how do you put people together in a virtual world? Maybe you have played games. You know that you connect to a server. You connect to a server, and then this is you have to cut the light here. I think this one. If you find it, yeah. And so to put people together, the normal classical way, you say, okay, let's connect to the people to the same server, and they are connected together. And when they are connected together, just like, okay, they're there. But the problem is that a server, it's just a server, has limits. At some point, I mean, your server is full, so you cannot put more people in there. So this is like the situation like today. And this has not improved a lot. I mean, this problem just arose in the 70s. There were the militaries in the US. I mean, they have these address emails in .mil at the end. They just started making research about virtual worlds, about the first step, and they had this problem. And actually, if you look now, I mean, things have not improved a lot. Maybe they are even worse. You can put less people together in a server. Why? Because you first the complexity of what you have to compute here is O n 2, where n is the number of avatars there. Why? Because you have to compute every interaction between each user. You have to look for everyone if there is an interaction. I am colliding. Things like that. So that means that the number of stuff that have been to be computed is n2. So if you have your processing power that is 100 times more, you only have you can put 10 times more avatar. But actually, it's not even the case, because since you need the computation, the expectations are higher. You have more pixels on your screen. Avatars are more detailed. You have more network, everything. So you need it's still N2, but actually the computation is even bigger. So things have not improved. And in, for example, Second Life, maybe you know Second Life? Yeah, Second Life, it was 10 years ago, it's still running. And but in Second Life, you can only put 50 people together. So more or less the number we're here, it's okay. But it's just that putting more, it's just not that work. And today, when typically in games you have 16 people, the normal stuff, maybe 20, very difficult to go higher. And there are solutions, though, to have a lot of people together in games. You know probably World of Warcraft, or so there are two classical ways of doing things. One is the region. The region, you just partition in region. So you say, no problem, I can scale. I can add more servers, so I have more regions, so I can put more people. Yeah, sure, you can put a lot of people, but not together. Just you haven't solved the problem of putting the people together. They're just in the region. So, and what happens with the region is that you have an issue. When you have a region, is that, for example, if you go on Second Life, you see that most the regions are called in Second Life, they're called islands, and most islands are empty, completely empty. So first is a kind of theorem. Say if a room is empty, it remains empty. Why? Because if you go with someplace there is nobody, you're not going to stay. If you enter here, you see a bunch of people, you just say, oh, cool. You just say. But if you open a room and there is nobody, what you do? You just leave. So, too bad. But sometimes there is some people in the room because you organize some event. You put, you're advertising it, you put it on Twitter, you put a web page, you say, Friday hacks and stuff like that, and people just start arriving. If this is physical, it's okay, we're just 20 people. But on the web, imagine on the web you say, yeah, there is some kind of cool stuff there. So people start arriving from all over the planet, and what happens? You say, no, guys, only 50, I don't want more people. It's just crazy. Facebook has 1 billion users. And you organize an event, and you just have to say to the people, just, no, you cannot go there. So they say, okay, so let's find another solution. And the other solution is what they call the shards of instances. But instances, people are not together. It's just instances, imagine that this is full. And instead of, when more people arrive, you say, no, just go to the other room there. And in the other room, we're going to make a video of of the talk in this room. So, you just go, you are alone in the room and say, no, what's the shit? So you just leave. So, and this is the shard stuff. The shard stuff, so it's, you just make a copy that is seemingly the same that the other, but it's not the other. You don't have the same people. And this is the shard stuff. Actually, the game designers have come up with stuff and make it a very compelling points. No, they invent, I mean, like a realm and a lot of things. I mean, even the shard name. I mean, shard is when, for example, when you broke a bottle, you have like shards. I mean, pieces of and it was a game designer, just Ultima Online, that came up with the game and say, I mean, you just like go to the same place and you don't find your friends. And you just say, oh, just because the universe broke in shards. And just like, it was like the game designer explaining that, I mean, actually, I cannot put everybody together. So I'm just like, make a story about that. And I mean, it's just like, the game designer are really great because they have, despite the limitation, they have found a way of doing it. So what I tried working on this problem like 20 years ago, and I just say, I want to solve that problem. And actually I found a solution. So let's go to scale. So what is scalability? What means scalability? Scalability, I mean, the normal stuff is say, yeah, I can only have like 50 people. It would be great if I could have 100. This is like a kind of scalability, no? We say it's case. No, so this is like what we're doing, but this is like, I mean, this is not like when they say Facebook scales. This is not the kind. Say no limit, and more people. Yeah, cool, come. The more you have, the better. This is like no limit for n. But this is not enough, because if you have like, when you have more people arriving, it becomes more and more expensive, or slow. This is not scalability. So you need like to have a constant marginal cost. Marginal cost in economy is called when you have like you make the investment, like you build the factory for cars, and then each car has a constant or even decreasing marginal cost. This is like you can have like mass production. You have scalability not in the computer science, but can you scale production of a car? When you have like the first prototype, and then scaling the production means that you start pushing more and more cars. And you have, I mean, when in industry they say to the scale, they say have a constant cost. So that means that the stuff has to be in OM. OM means like when you add one, the cost is of adding one is constant. So this is it. So this is like came up with exaQuark. So what you have that is that you have the here on the this is like an overlay. Instead of being a server, it's an overlay. An overlay, what is an overlay? An overlay is a kind of peer-to-peer system, but in the cloud. When you say peer-to-peer system, you imagine that everybody install an application and the application just talk one to another. You can have the same thing in the data center. Like, for example, Google FS, Google File System, it's just this kind of stuff. Oh, they just like have millions of computers and they are just connected in one file system. And this is like Google FS. So this is like this kind of stuff. This is an overlay, called an overlay. And an overlay is something that you can grow. Just is sure. I mean, an overlay is servers connected together. But if you need more, you can just grow more. So exaQuark here is an overlay. So that means that you have, when you add the avatars, you add more. There are more people arriving, 1 million, whatever. You just grow your overlay. And how this works, it's just because exaQuark works like this. You have, like, for example, here your client with your avatar, and you send your position updates. You say, I'm here, no, I'm here, now I'm here. You move all around, and the system just says what is around you. So that means that you have 1 million people, like 6 million people here, for example, in Singapore, and the exaQuark gives you the list of the people that is around you. I mean, it's like here, and then people are there, and there, and that's it. I don't need to have a connection with everybody in Singapore and everybody on the planet. I just need to have a connection with my neighbors. So the system gives you the neighbor, but the neighborhood needs to have a constant number of neighbors. Because if you have like, what neighborhood means, so we'll see on the next slides. But what is important here is that the neighborhood just provides you all the time a constant number of neighbors. If you have, imagine that, for example, they say, oh, what is the neighborhood? Let's take, for example, everybody that is, 10 meters from me, it's my neighborhood. 10 meters. 10 meters. If you are in here, it's okay. But if you are outside, 10 meters is not enough. I mean, there is someone there, 20 meters. I mean, 20 meters you can talk with someone. 20 meters. So you say, okay, let's put 20 meters. But maybe 20 meters is too much, because you are in a mass demonstration or a concert, and a 20-meter radius, you have like 1,000 people. So it's too much. So I say, okay, let's have so adjust the radius depending on how many people around. Doesn't work either. Because what happens? Imagine that you have a variation of density. So you are at the border of a crowd, for example. You are at the border of a crowd. So you say, oh, okay, let's put like 5 meters. It's okay. I have like a lot of people around me. And then you have someone arriving from afar that is 30 meters from there. Say, hello. I know you cannot see him because you say 5 meters. What's your neighborhood? And the other guy just has nobody around him, so he just have like 20 meters of radius. I say hello, hello, and you don't see him. So the neighborhood has to be. So this is it. Yeah. So first here, understand well that the point is that since you have your neighborhood have a constant number of neighbors, you have a constant number of computations, because you always have the same number of neighbors. It's not like when there are 1 million people, you have 1 million computations. No, you're in your neighborhood, there are 70 people in your neighborhood, you have 70 computations to do, 70 interactions to compute. That's it. Regardless if there is 1 billion people, or 100. So this is like very important. But also, your neighborhood needs a lot of things. You need first, okay, the number of neighbors has to be constant. The number of neighbors has to be not too small, because I mean, very easy to have a number of neighbors constant. 0, perfect. This is one perfect constant. Doesn't move, no computation, but it's completely not useful. So you need not too small to be useful. And you need also that the people that they are nearest has to be your neighbors. I mean, if it's not pointless. I mean, the person that is the nearest from you is not your neighbor. I mean, no, neighborhood, I mean, it's okay, can be anything, but you need at least that the people that are near you are in your neighborhood. So, you know, you need symmetric, means that if you are your neighbor, I am your neighbor, so we can talk one to another, we can interact. If I'm just your, I mean, it cannot be not symmetric. And also, this has to accept huge variations of density. This is like if you have, like, for example, uniform density, it works. Neighborhood, for example, the radius works, but in the real world, I mean, people tend to gather in places, and almost all places are empty. We look in this room, all that is empty, and we are just here together. And it's the same for cities. You have like deserts, the oceans, almost all the planet is empty, and people just gather in small places. There's the density, the variation is huge, and it's in power law. And even when they are in the city, people are in the city, and inside the cities, people tend to crowd again, with some limits, sure. And at some point, I mean, they are not. I mean, in the subway, they touch even so fast. So here. So then this is the neighborhood. The neighborhood, do you know this stuff, Voronoi? Have you studied that or not? So this is like, I'm going to show you how it works. Here, this line is it's equal distance from this point and this point. This line is equal distance from both points. And here, so this is it. No, this is built like this. This is a Voronoi cell, and here I say this is like neighborhood level 1, neighborhood level 2, neighborhood level 3, and so forth. You can do that. And this is symmetric. You see, this one is neighbor of this one is neighbor of this one. No problem. Voilà. So how many neighbors do you have when you use that? This is like for the number of neighbors of level 1. Here you have like the distribution. For random. So this is like this. How many do you have here? Here you have 7 for the neighbor from this one. So this is like here 7 that be there. And and this is like the distribution. So it means like it's not really constant. You can have theoretically, and you're sure you need at least 3. Impossible to have less than 3, but you can have like almost a lot. I mean, imagine everybody in circle around you, or everybody at equal distance from you in a circle, but this never happens. I mean, if you have like floating numbers, it's not possible. There's always one that is a near little bit. So, and actually, you should put people at, not at, a normal distribution. You got this stuff. It can happen, but I mean the probability is exactly 0. I mean the size of the set in which it's not the case is 0. Everybody you move everywhere, it's exactly there, exactly. Move a little bit off. So actually it's not. So this is like the probability. So this means like it's statistically bounded. It's like when you throw a coin like this. I mean, it could happen that it comes on the same size 1,000 times. What is the probability? Very low. Here it's not very low. It's exactly 0. It can happen, but it will never happen. Or like okay, doesn't matter. If you have more questions about what that means, I mean, about the mathematics of that. Yeah, sorry guys, I never studied computer science. I have a degree in math. And this is like if you have Delaunay 2, this is like the second level here, this level. This is like your distribution. So you have like usually less than 35, and level 3, 70. This is like the 70 comes from. Actually, we're using now. Actually, for using in exaQuark, we're not using a high.
How do you get that data?
Huh? This graph. I mean, you can make the proof, but actually, I don't need the proof. I just need to have the number. So I just you run a simulation and you got it. This is like you run it several times and you see how many neighbors you have, and that's it. Very easy. You just compute that once, second, many times, then you got that. I mean, this proof, the proof of average of Delaunay 1 is Delaunay is the name of the relation, this relation. No, this is when they are neighbor here, this is Delaunay. Delaunay, and the drawing, this is the Voronoi. But they are the same thing, and Boris Delaunay was the student of, I don't remember what the name of Voronoi, maybe Andrei Voronoi, I don't know, something like that. And so here you have this, so 4 and 5, okay, no, not 5. But this is you have this kind of distribution which that is statistically bounded. You don't have this don't have. So here, this is the architecture how it is implemented. So, because the point is that I just say you here, when we come back here, that this gives you a constant number of neighbors. So that means that you scale because you have a constant number of computation per avatar. But the point is that how do you compute those neighbors in a scalable way? Meaning in a way that it's with a marginal cost constant, a constant marginal cost in OM. So you need to compute this in OM also. So this is what the point. So first, I just like show you what is the relation. I mean the neighborhood relation. What is the one that allows what I'm saying to you? And now I'm going to show you how to compute this neighborhood relation in OM with a constant marginal cost. This is like second step. So this is it. So there is a distributed architecture that is actually it's 3 layered. I mean, actually 2 layers are enough in the algorithm, but for the implementation is with 3 layers. You will see. I will explain you how. So this is like here the neighborhood. Here it computes the neighborhood. You give your positions. Say I'm here. What are my neighbors? Please tell me my neighbors. And here you got the neighbors. So this is like an overlay here that computes the neighborhood. Here you have another overlay that. So what happens? You have here you are the programmer. You connect here to an entry point. The entry point you send your positions. The entry points give you back your neighbors, and you can talk with your neighbors using that. Because you send to another neighbor, then the other neighbor is connected to another entry point or to the same, but possibly to another entry point, and you can send a message. The kind of message you send is, for example, WebRTC signaling. I see you have a talk about WebRTC next week. So WebRTC signaling, and once you have WebRTC, you have peer-to-peer communication then happening here. So you don't need to use that anymore, but you need that first because it's good to know your neighbors. But actually, what counts is that you have to be able to communicate with your neighbors, to interact with them. So knowing the neighbors is not enough. You need to also interact. So to interact, you send first messages there, and then you set up a peer-to-peer connection. Peer-to-peer in the sense like a Skype call. So you have like a 3-layered overlay. Here it's really peer-to-peer. Here it's have another communication from entry point to entry point, and here you have a communication from zone to zone. So how it happens at the beginning? You just, first step, you call the allocator. The allocator just knows all the entry points. So it connects you to an entry point. Imagine there are more people arriving. No problem. Just launch another entry point. So you have more entry points. So you can scale, any entry points that you need. And here the allocator, it's very light. You can handle a lot of entry points. But if you need more allocator, you can just put more allocators. And you put more allocators, just replicas. This is like this is like a DNS server. No, a DNS server. You just say Google.com. Imagine that Google.com is not one computer. You just say Google.com, and Google.com, the DNS server from Google.com gives you an IP address, and the other guy gives another IP address. This is the same. You just connect here to the allocator, and it gives you an IP address or another IP address. The same. Actually, Google, as saying you Google FS is an overlay. That's why it scales. And here, when you are in the entry point, you just say, okay, I know your position. Now I go to the dispatcher, and I ask the dispatcher where I'm going to connect, to which zone I'm going to report the positions here of this object that is here. So the entry point is going to report some objects to one zone, other one to another zone, and who tell him what to do? The dispatcher. Because the dispatcher has a kind of map of all zones. He knows all zones. Actually, it just have a hint of how the zones look, and it just sends you to the right zone. It doesn't need to have an exact map of all the zones, just to know roughly how they are. I will show you that. So this is like I was explaining that already. So no way to get in. So if you have questions, you can go later. This is the dispatcher we're saying, and here it is. This is a zone. You see, in a zone, you have this is like the entry point. It's communicating here to the zone. It's sending the position. It sends the position here, and the zone sends the list of neighbors. So imagine that you are this little guy here. So you send your position, and the zone just know everybody that's around you, and it just send here the list of neighbors, because it's just computing that all the time. And this is like, this zone is responsible for that part. This color, the orange, this is the inner border, and these blue ones are the outer borders. The zone knows the outer borders, but it's not responsible. It's not answering questions for those. I mean, it's not giving the neighbors for those ones. It just knows because it's connected here to another zone, and they talk one to another. No? And so maybe here I'm going to launch some stuff. I don't know if I can find it. What is that? Yeah. I think it's going to open. No, I think the index is the one. Oh. Okay. This one was so. Yeah, this is it. This is it. So I need actually, go to reload. Yeah. So I'm going to show you here. So this is first there is something completely wild about Voronoi, is that it's very local, very, very local. This is why it's scaled. And I move here, you see? I move here, and it's not moving nothing, just in the very, very, very neighborhood. So that means that it can be like 1 million people around. When I move, it makes no difference for them. Because here, it just makes a difference for my nearest, the people that only for my neighbors. You see, the neighborhood is not going to change of shape because I got that. And also, what is kind of weird is that since it's so local, here you see this is like the zone here. Here is the zone, and here this is the outer border. I just put it one level. Actually, there are like 2 levels or even more levels. But here, just like for the sake of explanation, is only 1 level. And here, this zone is responsible for these points, but it knows here. These are the other from the other. But these points are unknown to this zone. This is like the millions there. You don't know it, but you don't need it actually. You see? You are here, and this one only knows here. And you see, I just ignored the other points, and the part that were in white didn't change. You just need to know the one that are in the border. You don't need to know all. You see what I mean? When I do that, it changed nothing. So you just need to know those points to compute it right. You don't need to know the others points. So you need to know just the one that are here, this zone. So the 2 zones are communicating in a way that here is giving that to it's like this. This is like I was saying here, and these points I'm going to give it to the neighboring zones, and the neighboring zone is going to give me these points, these coordinates. So like this, I can compute my stuff correctly, like I was saying here. And then here, what happens? when I say, yeah, but if he goes out of the zone, what happens? Yeah, what happens? So if you go out of the zone, you do like this, you're here, man, let me put it like this. So I'm here and go out of the zone. I don't know this zone, don't know anything, but the blue points around are me. So this one is going, it's moving, okay, you're walking, you go. And here what happens? Then say, oh, blue all around. This is not for me. No, now it's just said, oh, you neighboring zone, just take care of this guy. So now just like make the handover. So just make a handover. But actually this is like the handover is very, I mean, it happens in one step. But because I just like, I put in one point. But actually the real stuff is that you have several levels. So actually when you say it's arriving or entering the range, say, whoa, what's going on there? No? And you know already, so you are preparing yourself. So actually the transitions just go, you don't know, you don't see nothing because actually you are there here, the entry point is there and it's reporting the neighbors. So here you just arrive here, you continue reporting the neighbors, they are still correct, more or less. Not the third level is not correct. I mean the one that they are very far, you don't have all the data, but then chooks, it make the handover, and then this zone is just sending, another zone is just sending the stuff to the entry point. So the entry point don't even get it. And so imagine the client here. Makes no difference for him. So this is like the stuff works. And maybe I can make let's touch the presentation first. And so this is like it makes, and I was saying here, so here you have like the zones communicate one to another, not only when an object goes out, you see it's out of your hand, but also to make like load balancing and to keep the shape. Imagine that your zone is just like going like this, like a long succession. It's not good. So you want to have it like very like this. So when you have like a point that is still on the right place, but a little bit too spiky, the two zones just communicate, say, no, this one, I mean, I take care of this one, and you take care of this one. And so they just exchange points and they maintain the stuff. Or maybe there is too much activity there, whatever. So, I mean, too much computing power, say, no, I cannot anymore stand that. So I start sending to the others. So actually the zones change of shape all the time. And if there is like wild people arriving like crazy at some place, so the zone is going to shrink and it's going to maintain always the same number of people in there. So this is it. I'm going to show you a video of the simulation that is here. So it must be there. Yeah, full screen is Control F. No. Double click on the screen. Okay. No. So here you have like you see on the hopefully it's looping. So you see here you have a lot of tiny points, and I've drawn each time like the inner border in color, in the same color. And so if you go and you see like you have like densities in some places are very huge, and if you zoom in there, you will see like what's going on. The things are changing shapes. For example, you have this one here. You just probably just want to send it to here. So okay, here you have a simulation. You have all those dots and moving, like simulating people moving. And so this is like, so you see that it's in a sphere. Here you have here you have one zone, here another zone, here a big zone. Yeah, I think it was looping. So so you have like zone of different size, but each zone has more or less the same amount of users. So it's like a zone is per user. When you are in the server, for example, in the second life, in the region base, if a region is empty, you need a server. And if a region has 2 people, you need a server. If you have 50 people, you have only 1 server. And if you have 100 people, you cannot accommodate them. Here, if you have more people arriving, the zone are going to shrink, and you have more zones. And if you have like a huge empty place because nobody wants to go there, Pacific Ocean, you will have 1 zone covering. But they are also, they're changing size all the time. They are adapting. So, let's go ahead and view the slides. So I think it's over. Yeah, no, it's not over. So this is okay. This is like you have like kind of the proof of the algorithm. I mean, just like drawing on heavy mathematical proof, but I mean, you can read the paper if you want it, but it's just like to make you understand how it's. But then I made a simulation, and now I'm preparing another one with a lot more. I want to have like a million avatars together. But this one, I'm not sure I'm going to find it, but I mean, in that time, this one was like 4 years ago, and I just had 50 CPUs to run the whole stuff, because I mean, 50 VMs, I mean, 5 years ago, they were expensive. 50 VM, I mean, you need like a little budget to do that. Now 50 VMs, I mean, a VM costs per hour like 2 cents. So I mean, if you want, like, if I need like want to run something with 1,000 VMs or more, I mean, maybe it will cost me like $10. Okay, yeah. So it's not much. And so, but in that it was like this is like some years ago. So it was like 40 CPUs, and I made 30,000 simulated avatars. I mean, like real people, but not with the real people, because it's not easy to find 30,000 people who need like have a very successful game or a lot of friends. And and there were 2 kinds of scenarios. One was social virtual world. It's just like for interacting. It's the talk and stuff like that. And the other one, action game, and it needs like more speed. And also the simulation was kind of realistic. You also already saw the sphere, the kind of simulation. So mimicking, I mean, was taking from 2 sets of data: the human mobility, the way of people move, and the way of avatar. They are quite similar in virtual worlds of the way of people move. That is actually people tend first to gather in places. I was already saying that. I mean, they tend to gather in places. I mean, there are places that they are, I mean, infinitely more crowded. This is like a Pareto distribution. It's not an average. Earth has so many people. No, average has no meaning. Actually, there are places where everybody is and places where nobody is. You have like the long tail. Say most places are empty. The few places are full. And this is like the distribution of people. And there is another one that is people tend to do like this. They have a power law distribution of mobility. Usually, you don't move. You don't move, guys. You sit, you don't move. You sit. This is like the most of your time you don't move at all. And sometimes you just move. Go to the bathroom, go to the kitchen, take the glass, and then you sit again. That's it. And then once in a day, on the day, you just go out and go like for 2-3 kilometers out, you go to work or whatever, or to the movies, do something, and then this time you then stop moving for a long time. And then you move again. And once a year, you just take a plane and you go all over the planet and do like that. And it's you have this kind of mobility that is also follows the power law. And even worse, the people distributed like in a power law. Most of the people on the planet never leave their village. They just stay there all their life. Or they never, and there are some people that take a plane like once in their life, and people that take the plane like once a month or once a year. I'm in the once a year category, and you have people that take the plane like every month, and people that take the plane every day. I mean, more than that, no. So that means that the people distribute that way also. So then this is like the basic way of they were moving here. So instead of so I had teleportation movements, and people were just gathering in very dense place. So this is like the way the simulation was running, and the one that you saw on the sphere on the video was this one. So here, just make this is like the results of the simulation, and here it shows that when there is only one zone, you can put 5,000 avatars. I mean, in that time, hopefully now it's better because we have like running better. If you have one zone, you can put 5,000 avatars in the social world scenario. The social world scenario is one update every 4 seconds. That means that if someone shows up there, coming from afar, I mean, I see people there, and I will know maybe 4 seconds late that this person have shown up. Then, I mean, once it's my neighbor, it's just like updating at fast pace, no problem. But I mean, this is like for knowing, it's the updates of the neighborhoods. Neighborhood updates, actually I should have written neighborhood updates every 4 seconds. So I mean, in average, I can have like 2 seconds of delay knowing that someone is arriving. And then when there is one zone, it's only, I can have like 5,000. When there is 2 zones, actually it drops because I have I have the intra, I mean the inner border and the outer border. So I have like more, I have double computation of stuff, and also I have communication between the two zones. So it's normal, it drops, but then stay stable. That means that if I go here and I put many, the cost per avatar is constant. Done. This is it. I mean, this is the moment I just said, investor, give me a moment. So, problem solved. This is it. So you have more or less the same stuff, but with updates, fast pace, and here you have only like 1,000. So the number of avatar per zones, but it's also, actually, this is, maybe it's not constant. I don't know. I need more, but it's just like of optimization. So it really goes down very, very, very slowly. Actually, there's this kind of algorithmic leak that is in the heuristic, but you can improve the heuristic. The heuristic of, the dispatcher, it sends you to the right zone. Don't make a mistake. When you make a mistake, you have a leak. You have a minute just gone down. But this is, you can, I mean, have a better, and I mean, you can improve your heuristic. So the leak, you can make it as little as, I mean, you can improve it. So you have basically no leak. Means the leak is like the flow that is going down very, very, very slowly. So I think now I'm done. Yeah, and what we can do with that? This is what we can do with that. Is that actually I just started this stuff. Yeah, let's solve the problem for virtual worlds and then. But actually, in the real world, you also have position. I mean, all the example I was talking to you was in the real world. I said, I move here, I move here. There. So what's going on? So imagine that you have like drones here. Put a drone. You will see it can be more than drones. I have a drone, and you send your position. The drone say, I'm here, and exaQuark just say, oh, you have those drones around you. So that means that you can avoid collision. So, and how do you work to avoid to avoid collision. You have what's called sense and avoid. Is that when you have like they are just flying, they don't talk, no connections, like the planes now, and more or less like this, and they just like, and when they arrive in sight, they have a radar, a stuff, and things start ringing all over, alarm, boop, 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 there is a plane nearby, I mean, where? And then they do, and say, just the last moment stuff. This is like sense and avoid. They call it in avionics, they say sense and avoid. This is like last emergency stuff. So they say, no, this is too bad, this is too dangerous, I mean, we can't do that. So they are slowly trying to implement proximity communication. So proximity communication, they have like Wi-Fi or something, and they started talking together when they are like 100 meters apart. They have like the video, start talking. But this is something crazy. They only can talk to avoid collision when they are nearby. So that means that to avoid collision, they have to approach one to another. I mean, it just makes no sense. So, and this is why if you use, for example, exaQuark, everybody just assume that every plane has to have a connection, an internet connection, that hopefully is going to happen, or every drone is going to happen because you have the 4G. Actually, if you are in a plane, say, just put in airplane mode. Just don't do it. I mean, it makes no sense. And you just on the plane and look at the 4G. You will see you get a 4G everywhere. I mean, not when you are flying on the ocean, but when you are flying over a country, usually you have 4G. Maybe you cannot make phone calls, but sending data usually it works on the Earth because, and it's just like not intended stuff. Because the antennas are not pointing to the sky, I mean, they are pointing to the ground. But even though, I mean, you just like have enough to get the signal. And 5G, they are intended for planes and stuff like that. Because I say you have 4G, but the problem with 4G is that when a plane just go too fast and you change from one antenna to another, what is called handover in cellular telephony, the handover does not happen well because you are flying too fast. So you don't get the time to get the connection before you lose it. So that means that you lose your connection and start again another connection. No, but I mean it's just like with 5G you will have like a normal connection. So that means that this is going to happen, this kind of stuff. But if you have like a server, you have to report it. I mean, if the servers actually just can handle like 1,000 stuff, and if you have like millions of drones, I mean, it's not going to work. So that means this is doing this kind of stuff. So actually, I was in there were one time. Where am I? Okay, just like taking over time. And so this is like, but actually you can do that for everything that is in the real world. So that's why we call that spatial networking, because it's like you make a communication with the people that they are nearby. For example, if you have like, you see the people there, outside there, or even you, I mean, and there is only one way I can make a communication with you, is by using a physical name. Can be an airwave, can be or I can shout and talk very loud, and when the people there have to open the door and say hello. I mean, they all have 4G phones and Wi-Fi, everything, computers, every stuff. I mean, I cannot call anyone there. I cannot. The only way I can do it is just say open the door. This is crazy, no? I mean, there's something missing. So this is, if everybody, like I say, who is there? Oh, I can see the people there. Let me call this person. Without opening the door. She or he has a phone. It's a connection. What's the point? Why cannot call? So this is like the stuff, and this is what the company now. If you want to go, there is an SDK for developer. It's already running. We have like 2 developers, which is opening like 1 minute. Not a lot of people. Is there? exaQuark.com. Maybe I can show you also what I've done using that. I saw the put this here. And we have to push it there. So this is like it's grouping, David? Okay. So this is on Oculus Rift. So you put your headset, you are immersed like this. Cedric, have you seen that?
Yes. You didn't bring it.
Huh?
You didn't bring it.
No, I mean, it's too heavy. And to set up the stuff, you need internet connection, everything, and you have to write like 1 hour before. And so, and then you go and you see the other people. They're teleporting. This is like I've called it. I mean, just like by myself. I mean, it's not. It's like let's say a student project, something like that. I'm not a student anymore. Maybe I'm a student for life. Like this. And you have like voice. I mean, you can talk with the people. I mean, with the people around you. And more or less that's it. And you can travel everywhere on the planet. And you can walk around there. You can walk and this is like, oh yeah, you can do crazy. But actually, this is like if you go on the page, this is divereal.com. You can go if you have an Oculus Rift, you can try it. It's there. I mean, it's on the store. Just go on divereal.com. And here, do you have an internet connection? Yes. Then you just go on exaQuark. You go on exaQuark. exaQuark.com. Oh, we don't see it. Here there is like a volume, but in this screen you don't see nothing. We see it here, we see, but not it's there. Oh yeah, oh there. Oh, if you look there, this is like the website here. This is like the screen is so small that is like this is like the phone, version. Oh, you have here the menu. Oh, this is small. Now I have to do it with the finger.
This is right click here.
Oh, yeah. Okay. So you have, and so you can go there. You have like the code, documentation, SDK, everything, and you can use it. It's open source. And so for the moment, we don't even have an API key. So we have people developing using the stuff. We don't know who is that. We just see like, I mean, there's some traffic going on the platform. Somebody is using it. Who? We don't know.
Okay.
Yeah, actually, it's funny because you can choose your real location. So we know the guy is in Romania, but we don't know nothing about him. I mean, maybe he's in Romania. Maybe it was a different location. We don't know for sure. But it looks like he's in Romania. So we had one guy from Romania trying the stuff. But I mean, just like people like calling him all the day, so we haven't. We want the things running before controlling the users, and we didn't expect to have people using it, but we have to say, oh, cool, there's an API. So if you guys want to do something, you can do that. So and this is so you can use the okay. And if you have questions, and actually, we're going to release a sample application. And so when it's ready, we'll send it to you so we can forward it. And we're looking for the vision or something like that, or the video. Yeah, this one is here. I think it's the I do here. Oh yeah, but this screen is not. What about that?
exaQuark.com/. pictures.
Yeah, but I don't know why it's not. I think this one is just like, where is that? Kubernetes is in the menu normally.
Okay.
Yeah.
Okay.
Yeah, this is it.
Yeah.
But, yeah. This is augmented reality stuff.
Are there other production systems using this technique?
There are things similar based on servers. I mean that they are just like you can put the server numbers, but they, for example, the one that is most used is one that is called that is more or less the same stuff, but instead of giving your neighborhoods, it gives you 100 people that are connected on the server. But because actually I was just like saying you that to put people together, you put it on the server. But actually, servers usually do more than putting people together. They just compute for you a lot of things. Instead of you computing on your computer, you make it like this. So actually, when you know the lag, when you have a lag in a virtual world, what is the lag? The lag is just actually when you. It's not like you say to your avatar, move. It's not happen like this. You just say to the server, I want to move there. And the server says, no, you cannot because there is a wall in front of you. But you have to wait before moving. You have to wait to the server to compute for you the physics of the wall, to make the simulation run. So, for example, in Second Life, the servers are called sims, simulators. And actually, it's just like I think they have other stuff. I don't know if this is common. This is weird because I'm from Venezuela, and this is a flag from Venezuela. And I just like, I don't know how it happens that, I mean, they say, wow, what's that? I mean, there's a flag from Venezuela. And after, no? We didn't shoot the video because of that, and there is a flag from Venezuela. I recognize the flag, you know, this is our kid, they put you have to see him in the antenna in front of the flag, you know, the flag very well. But just say, wow, the flag. And so the thing that, for example, you have, so there are others that they call that they say like you have peer-to-peer communication is that they use this kind of stuff. And it's, for example, the lag. I was talking to you the lag that you have the normal lag. That's why you have. I want to have a big ping to the server ping because actually what counts is that, for example, if you are playing a game that you shoot people. When you just say to the server, I'm killing that guy. So the one that just, if you are just in front of him, push like this at the same time, but the first one to reach the server is the one that wants. So that's why you need a ping, and you don't want to have a lag. It means you don't have to have a long pass to the server, and if the server has to be faster, so it computes faster. But there is still a lag, always there is a lag. And when you are in virtual reality with a headset, when you have a lag, it's like you have a lag in reality. It gives you sickness, I mean, motion sickness. I mean, the lag is not, you cannot stand the lag. So they stop using servers and they put like a peer-to-peer stuff, you know, with direct communication. So you have no lag in interaction. But that means that, for example, you cannot shoot people because there is not a server to make it. So it makes a little bit different of what you can do or the way you can do the things. You make it a little bit different. But the problem is they are not scaling either, but they are using this peer-to-peer communication. So the trick of the peer-to-peer communication is very common. The one that makes very different in that technology is that first neighborhood, instead of putting all the people that are in the server, actually there cannot be a lot of people in the server, so they give you all, right? That's the point. But then you have like the neighborhood stuff that allows you, I think I have more videos, so I'm going to show another one, just to change it. And so what I was saying, so the point is that you have neighborhood, so you have this idea of neighborhood, and the distribution, the overlay that makes you can have a lot of people together. So once, this is like the two things that they are different. So actually, just like for now, today, you want to put people together, you can put 100 people together. I mean, like for example, GTA 5 is 16 together. Most in every game is 16, but sometimes you can go up to 100, or if you slow things very well, a lot, like in even line, you're gonna have like, let's say 10,000, but actually very slow. Or when the game is very, you have very little interaction with others. For example, World of Tanks. World of Tanks, actually, they have a neighborhood notion, and you have very little interaction, just like the direction, the position. And actually, in World of Tanks, even using using a server, they have their own servers, they can have battles with thousands of tanks. Actually, that's yeah.
Just wondering, how would exaQuark scale? Because you mentioned drones, right? There's still a z-axis, right? So how?
The one, 3 axes.
Yeah.
Yeah, actually, just put 2 axes because it was easy to show in the slide, but actually, it's in 3 dimensions. It's very exists in 3 dimensions. So instead of having fast thing, it's like this. But basically, it's not exactly 3 dimensions. It's like, I would say, like 2.1, because actually we just like stay flat. It's not like just flying all the time. And even when we fly, we stay very, very, not very high. It's not like a battle. It could work, no, but basically not on Earth. And not in virtual games. Because actually, when we are just used to moving 2 dimensions, when we start moving in 3 dimensions, it's very complicated. Just to have it. We are not birds, I mean, no fish. We don't know that. We just usually just stay flat. So even if we go a little bit up, it's not that much. Maybe in the beginning, you have like slow layers, but even though, I mean, you have like, you can go up like less than 1 kilometer, and on Earth you can go like 7 kilometers. So it's just like mostly flat. I mean, in 2 dimensions. But it's actually it's implemented in 3 dimensions. It's in 3, you have the Voronoi in 2 dimensions.
So near the border of the zone, like if I look up into another zone, will I see?
No, actually, it's, you don't look at another zone. The zone just computes for you the neighbors.
Oh, I see.
Yeah, just compute you for you the neighbors. So what can happen is that when you are in the border of the zone, if you are just in the inner border, no problem. But if the moment you cross, you can have like all your neighbors are not correct. The time you make you see the neighbors normally, I mean, they are moving, the one that you see, but maybe there are neighbors that are missing because you are not yet on the new zone, so you don't have your neighbors. Not your immediate neighbors, but the not the. You are here, for example, so you move here. Once you are here, you have all your neighbors around you. The 3 levels of neighborhood. 1, 2, 3, no problem. You have your levels of neighborhood around you. You are here, for example, you have 1, 2, and 3. So you know your neighbors. But then imagine when you move here. You move here, so you are missing because you only have like 1, 2, 3. You don't know this one yet because you are connected to this zone. This zone only knows here the blue, but don't know the white. So you are here, for example, you move here, and you don't know yet these neighbors. But it's just like you don't know the last layer of neighbors. The neighbors that they are further, there can be a delay before you know those neighbors. The delay is around 1 second. The time you switch from one zone to another. And actually, you are not reporting your data so often to the zone. So that means that actually the updates, the range of updates of your neighborhood are probably lower than the delay of moving from one zone to another. So this is not going to impact you. It's not like, this is like you are making the analogy of the region-based stuff. In the region-based, what happens is when you are right at the border, maybe you can see what is the other one, but you cannot interact what is on the other side. No? But here it's not such stuff.
So so a client is only so a client within a zone only knows like a small part of the zone. It's like
yeah, he knows he knows all the people there. Actually, what is static, you just download everything that is static. I mean, no problem. Like for example, you see in Ivory when the people were in the planet, moving on the planet, going to Paris and so on. Yeah, I mean, you just download everything. Everybody, or you have like the DVD with the zone. I mean, no issue. The point is that are you aware of the people that are around you or not? If you are aware of the people that are around you, you can play with them, you can talk with them, you can do everything. And the point is that if someone shows up, I mean, far away in the neighborhood, you can have a delay before you know it. That the people appear. You have a delay anyhow. I mean, you cannot be instant. You just need to depending on your kind of game, which delay you want to know that someone just shows up in your neighborhood. And the lag, because you move from one zone to another, or because the other guy is just like moving on your zone, this lag is very low. It's not it's not like they need to load something. They just say, no, from now on, you take responsibility for this stuff. So it's just like exchange a message to here, and then he starts sending his UDP packet to the entry point here. It's another zone. So this zone says, now you are going to report to this entry point. I'm not taking care anymore of that guy. So it's 10, and it's just start sending that, and the entry point says, I'm going to now to send the packet to this one. So instead of the entry point just starts receiving packets here, so it started making that. This is like you are talking how the handover is going on. But the handover is it takes like, you say one here, and then you start doing here. So it's just like, instead of having one hop, you have one more hop, and you do. So nothing. Just and it's just the handover is done, and then you start playing before. So the handover, just like you have like one more, but this is like this is not like on the wild on the internet. This is inside the data center. So this means you have like you have no lag, the ping is just like below 1 millisecond. So it's like it's happening inside. So no problem. It's not like when you move from one region to another that you have to connect to that region. You have to load things from that region and stuff like that. This is just like send the UDP doesn't run, and that's it. Very, very light stuff. And actually, I was just like making the difference, the cost, the difference of cost. And one, and it's like there's a factor like 10,000 or something like that. There is 1,000x the cheaper this one because there's so little computation in the cloud. So actually, we just bring it free. We don't like Facebook. Facebook don't charge. There's another more question. There's another presentation. More.
So I guess we'll we'll get Johannes to present on Kubernetes. Kubernetes. Yes. So thank you, Joaquín, for your insightful talk. Sorry for
I carry my laptop.
So you can't have the definition of neighborhood is different.
Yeah.
It's still running?
Yeah.
No, but now I see,
I think so.
it's not running anymore.
No, I never check.
Maybe your memory full already.
No, it's not. It's live. What? Live stream. Why would it be full?
Yeah, but my Facebook says, oh, it's still live? Hey, what comes your
Webcast.
So we cannot have an action game where there are sniper as well as short range shooting.
Maybe the bullet would have like a zone. The bullet would travel. But then if you're able to see the enemy, then I guess you are within the range. Yeah, you know what I mean.
Yeah, but like
You might not be able to see the sniper, but you are supposed to be able to perceive getting hit by it. Yes.
Populate a big world.
Like if you're saying like a sniper will be able to see you, but you might not be able to see the sniper, then will you still get killed by the?
Symmetry.
Yeah. So you would.
No, but then the issue you're talking about is like if I fire and you fire at the same time, right? So you turn around the corner and
Yeah, this is like
fire at the same time, right? I mean, there is no way of resolving like who hit first.
Yeah, so that's what you make if you have a referee. It's like when you have a sports, like football.
If online they do time dilation and then they
So they
process
process everything, and then so 1 second happens in like 100 seconds. So
the process where each projectile
Yeah.
who gets hit in what order.
yeah, and that's how they make it to have like 10,000 people together because they slow down time by 100. That's right. So 1 second is just like you do it, it's shoot, and then you have the laser just moving like
You go get a coffee.
If it's on.
Yeah, you play, you don't play.
No. Like I don't have that much time to wait for my results.
presents out
Yeah, this is another thing. It's a peer-to-peer simulation. People just assume they need the server, and actually you need the server for very little. You need the server for non-commutative actions. It means, for example, when you move, for example, imagine that I perceive something and he perceives that. And move. So this is I know here. And he just perceived that before and you move. So what I will see is that I move and then you move. You will see. You move and then I move.
No, it's fine.
What happens? I mean, at the end, we same thing happens. We don't know that the other has seen another thing happen. Just like this is like commutative action. I mean, if the order doesn't impact the result. So this is commutative action. But when you shoot someone, it's not a commutative action because I kill you, you kill me. It's not the same thing. Because if I die, I cannot kill you. So this is like this is a non-commutative action. But actually,
I think in some games you're supposed to kill each other.
yeah, you can make it commutative. Why? Because it's cheaper to make this kind of stuff. It costs you less computing power.
Yeah, I used to play games where you kill each other.
so you stay alive for 2-3 seconds after that.
Yeah, so it's possible. So just like shoot, and then what I say, no, I shoot first. I mean,
I remember like very old FPS. Like I think it's possible to kill each other.
yeah.
I remember.
So this is but for example, when you push someone, this is not commutative stuff. So there are, but most actions that you do are commutative, and even more if you are like just interacting with people, you're just talking with people, not interacting. It's commutative. It's non-commutative is when you start fighting for something. I mean, you eat a pizza, I cannot eat a pizza. I mean, it's just like if I eat first, you cannot eat second. This is not commutative, but this is like when you start fighting. I mean, when they don't fight, I mean, just talk. It's okay. Or just and then
obviously contributed. I didn't get this last year's one.
Yeah, but
Is it?
purple color one.
Purple and usually
I'm very happy that I decided to make my 3 pull requests to myself. Kubernetes. So you can introduce verbally.
Use the whiteboard.
Yeah.
Use the whiteboard.
yeah, this is Windows.
Yes.
Login screen.
Okay, let me see this. 5 minutes. Then
Do anyone of you have the Mac?
Google Slides there.
No, I don't have. Mine's in the office. Why? What's wrong?
I don't make help.
Wait, nobody has the dongle?
Yes, but doesn't work.
So bad.
You there? The one that-
Hey, that one was. We can watch.
Yeah, but actually, it's not only a dongle. And for me, it was not a dongle issue. I think that the resolution of the projector was too low, and the Mac was not handling the stuff.
Smart Nation, man. We should upgrade.
Yeah, it's small. It's like,
Johannes, you're using Windows.
I'm using Linux.
Linux, okay. That makes more sense.
I'm projecting from
I am demonstrating
what?
Kubernetes.
Kubernetes or Windows?
Just go hangouts to my.
Yeah.
Virtual box.
Are you using Hangouts to communicate between the two?
Cool.
Ex-
Seriously?
Extreme.
So it goes all the way to a Google server. It comes back.
Yeah, goes to California.
No. I think there's a server here at the data center. So I think it's not that bad. But it's like, it's still further than the two screens.
It's like exactly the problem that you're saying, mentioning is now.
It's like in the past, you put CloudFront in front of your website, right? In Singapore. So like to access your website in Singapore, you have to go to the CloudFront server and come back.
How do you tell? I don't think so. I think it's just showing black.
What?
Wow, like showing black. I mean, this is like a dark net.
No, if it was showing black, it would still be light.
Maybe we go there.
Yeah, maybe it's
It works.
Yes, digital teleportation. No, but this is like.
This
is my stuff.
No, it's like
We are teleported to 1991.
Before the web.
Show it.
Can you
okay, it works now.
Woo! Okay. No!
It's not auto connected.
This is awesome.
Yeah, so let me talk about all stuff. When I sent my first email,
When was this? 1990. 83. Wow.
in 83, who was
That's like Kobe's before I was born.
Hey, let's go.
Even I was
Yeah, actually, in that time there were no internet. It was like connected. There were like two stuff.
The doves.
It was ARPANET, and ARPANET was the military one. ARPA, Advanced Research stuff, and the other one was BitNet. BitNet and ARPANET, they were just like fighting, trying to make another one. There was not ARPANET, but at the end, everyone merged on ARPANET. So, but you could connect to BitNet or to ARPANET. And actually, where you were not using, it was not the email, was handled something like his UUCP or something like that.
was the first
Unix to Unix copy or something. This is like there was a kind of protocol that you copy the email from one machine to another.
Are they calling themselves?
There were no FTPs. They were just like email and news groups.
High tech, low tech.
And the first thing that were news groups.
I don't understand.
It's the high tech, low tech.
Build an interplanetary network system just to have
Yeah,
screen broadcast to the other.
Yeah, interplanetary stuff. I mean, this is like in the imagination. This is in the at the beginning of the 60s. The interplanetary. No. This is like the first name of the internet.
Oh.
You don't know that? I mean,
No,
Yeah,
the internet is
Actually,
no, but because the guy that just give the money to Drew Engelbart, that was the guy at ARPA, that was the league leader. He just come up with an idea that was the interplanetary network. And this is like and it was just like an email, but on paper, just talking with his colleague about the interplanetary. or intergalactic or something like that. I don't remember, just crazy stuff. And then when Joe Grindelwald just arrived and just say, I'm going to implement that. You just say, wow. So we just keep giving the money.
Okay, you know what?
There's a new law.
And it was just a bunch of people taking LSD. Yeah, not that. You want the slide about the story of internet? Yes, I've been teaching story. Yes, history of internet.
Yes, please send me the slide on Slack.
And what are you going to do? We are going to
This is, guys.
Yes, okay, got it.
This is being streamed online, right?
What?
This is
Yeah,
being
yeah.
streamed online.
Yeah.
He's streaming his screen to another computer using Google Hangouts.
Okay, share your screen.
So romantic.
and because you don't have a do you want an USB to make stuff? Maybe a diskette, a floppy disk.
It's terrible, guys. Come on.
Yes.
Networking.
Who has played with Kubernetes? This is such a small group. Who has played with Kubernetes?
Only red.
Red.
Red is like, I don't really need this. It's like, I would have like 100 concurrent users. Open PC. Something share.
For GK.
For Kubernetes.
For group, Kubernetes.
Yes.
GK, I assume. Google Cloud.
Yeah.
They're using Kubernetes.
What's the like? Really?
When you say large.
But Grab has several outages.
Outage.
Okay, hi.
Carousel
Yes,
also recently.
So this is basically like baby steps baby steps to starting using Kubernetes, which you probably also will have will encounter as well. So I'm just going to talk about a little bit about what is container orchestration, then the key concepts. A very quick overview of key concepts. Then after that, I'll just start discussing about creating a Docker image and trying to deploy it online at the website. So container orchestration. So traditionally, when you deploy an application into production on the cloud, your application's configuration is tied to your operating system, tied to the kind of resources your operating system gives you. What the past couple of years, there's been a trend towards containerized deployment, where basically you encapsulate all your application and software dependencies into one image file, and you can deploy the image file to a lot of different cloud platforms that support hosting these image files. What you have is that your environments between your different applications running on the same machine, the environments are distinct, and they each see their own environment. So you don't have applications interfering with one another. And with containers, you can sort of automate recovery from when let's say a machine or a VM fails, you can have the container orchestration sort of do that for you for a variety of different apps, rather than the more ad hoc ways of recovering from a node failure, say with Puppet or Ansible, where you might have to orchestrate things differently, and for each different application. So the containerized, so what containers allow you to do is to separate your applications from the kinds of resources that you need. So so with containers, right? Your resources are more like you have a compute resource, you have a storage resource, you have a bandwidth resource, and from the perspective of like allocating resources to your containers, we can more sort of like generalize all the different hardware resources that you have into these three categories, and just use your use your orchestration system to sort of like say, hey, I want this amount of compute, hey, I want this amount of storage, I want this amount of bandwidth, and you'll find a way to allocate that for you. So this is like the revolution of containers. So in Kubernetes there are like three kinds of ways to sort of like use Kubernetes. Sorry, more like two kinds of ways to use Kubernetes. Turnkey solution providers, vendors, they have their own like optimized their own version of like the infrastructure, their own version of infrastructure and software that provides Kubernetes, and you just sort of like provision your own Kubernetes cluster using their APIs. And as you'll see later, they typically have some idiosyncrasies or custom features that you might not expect from when you are trying, like say, your own deployment. If you have like special requirements, you'll need to like, and you want to host it yourself. The standard solution, or rather the get feedback solution, is to use these two tools, kubeadm and kubelet, kubeadmin and kubelet, to provision and configure your own cluster. And if you're like some big company or you have like very interesting requirements, then you probably want to use a custom solution, or rather develop your custom solution. But for most of us, and for most purposes and businesses, you just use a turnkey solution. Then when you are like trying to test the deployment or test, or if you are when you want to try to test a deployment, or when you're trying out Kubernetes, usually you start off with Minikube, which is like sort of like a collection of utilities and interfaces cobbled together to provide a Kubernetes environment, to provide a Kubernetes cluster-like interface. So it's a single node, which means that usually you run Minikube using like say using either an interface that makes your computer a node, or using a VM solution, or using a VM. So like say you'll configure this with like a VirtualBox, and you create a virtual and you provision and you create a virtual machine or a VirtualBox that acts like a Kubernetes node. And so this is for like getting your hands wet and like say debugging some deployments before committing it to a deployment in the cloud. So yeah, so unless you have like interesting requirements, you should usually only be using like turnkey solutions, and maybe like trying stuff out locally using Minikube. So what is a Kubernetes cluster? A Kubernetes cluster is basically this. Okay, you can just think of it as a cluster. You can think of it.
Can I ask a question on the spot?
Yes.
I was wondering, yesterday I just want to install the stuff and the overlay, and I need to compile some piece of code, because it's the one that is in the library in C++, and the piece of code in C++ that makes the computation of the role. So I just compiled it for the target machine.
Yeah.
And I mean, I have to compile it every time and change from one machine to another for two reasons. Because my binary is not going to run. It's the first, okay, my virtual machine maybe is going to run, but I have to compile it for this virtual machine anyhow. And then I can move to a similar one. But I mean, if I want my stuff to be optimized, I have to recompile because the compiler has optimization options. It looks what is available there on the processor and makes stuff. Sometimes it can parallelize and
ask like how does that work?
yeah. So is that what happens there? Okay.
This ultimately this won't be a solution for that.
It's not. This is like only for generic stuff. You use only generic piece of software. This
is
Python, MongoDB, and stuff like that.
Yeah. Okay. It's very generic. You can't you can't be guaranteed that programs compiled to exploit certain certain processor features will be able to run in this.
Yeah. Do you mean? I mean, for C++, it's not a good idea. It's just good for Node.js,
for C++,
Python, and stuff like this.
Yeah. Yes. Like for C++, it really isn't. I don't think this is a good idea.
Okay. So this is just no, but it's important just to say. So it's good if you have your stuff on Node.js or PyPy or something.
Yes. Generally, like stuff that isn't very that doesn't need to eke out every single inch of performance on your sorry. So you have applications that are high performance, right? Yeah. This isn't very good for those kind of applications.
You don't run those.
No, yeah. But
this is
even virtual machines. It's better than that.
So this is more of a solution for say where you are providing a complex service, like you have different databases of different kinds of stuff, and you are serving to a lot of users, but it isn't as real time as what you need. Isn't as real time as what you need. Let's say if you're like Amazon and you need to aggregate data from a lot of sources, and the throughput is still very big, but it is not as instantaneous as like in the game. So in this way, this is like you can parallelize it. Using this, you can parallelize it and manage like much higher throughput. Because like say if like one machine failed, if you have like 1,000 machines running the same service to achieve high throughput, there's a high chance that one machine will fail. And so you want to give your users if one machine fails, it's not going to destroy your service. So this is good for reliability.
Yeah, this is the distribution. This is the
idea
of distribution.
Yeah.
When you distribute it, exactly.
Yeah. So so with Kubernetes, you have this concept. So a cluster is basically a couple of nodes. Nodes basically are an abstraction of like the machine that you are running on. So they can be virtual machines, they can be bare metal, they can be maybe funny stuff that sort of like abstracts two machines as one or something else. But in a sense, a node is a representation of the machine. Then what you are going to deploy are containers. So containers, like I said, they are images of the applications that are going to run. And when you deploy them, you basically execute them as what I call an app instance. So a cluster is something that provides multiple services to multiple services, and each service might be like a web application or database service. And so we abstract the idea of providing a service from the machines and the applications that provide it into a notion of a service. And declare it as something that our cluster provides. So then behind the services are the things that actually implement the service. which are pods. So each pod is an instance of one or more containers that provide a service. So like say you can have within a pod, you might have associated with it an image of Rails with some configuration and some authentication files to connect to the other services and configuration. So that's a pod, and a deployment is basically describes how many pods you want to deploy, and maybe say you want to have some affinity of some pods to some machine or some pods to some other pods. So these are the key concepts, and so this is a picture of a cluster of 2 nodes, and so each node, and so actually these services should be sort of abstracted out of the node. So each node provides, or rather, there's a service above these 2 nodes or rather a layer of services above these 2 nodes that the pods within each node provides. So the idea of pods is that the pods are ephemeral. You don't really care about whether each single pod is healthy. The idea is that if you kill a pod, the other pod should be able to pick up the slack and behave as if and provide the service as if nothing really happened behind. And so and behind your deployment should include should be able to describe well enough the pods that you're going to deploy to notice that, hey, if a pod is failing, just kill it and it will spin up another new one. So so basically your deployment will tell the orchestrator to, or rather the orchestrator will automatically handle this when you have configured deployment. So I'll go through sample files of the various deployments data, but so right now I just want to talk about what you're going to see when you go to what the major programs you're going to see when you go to the Kubernetes page are. So so I previously talked about Kube admin and kubelet. So basically what makes a Kubernetes node is basically this daemon running on it. So it's a daemon that sort of interacts with the other nodes to say and manages all the admin stuff that Kube node has to manage. I'm not very sure on what exactly it does, but it's basically the daemon that runs on every Kubernetes node. QAdmin is a tool if you want to roll your own Kubernetes solution. So it is basically a tool to set up and administer your Kubernetes cluster. But the tool that you are going to interact with most is, or rather, you will hardly ever use this tool. You hardly ever have to run or use these two programs, but you'll be using this tool a lot. kubectl basically communicates with your Kubernetes cluster, and it's how you communicate to a Kubernetes cluster. Hey, I want you to fetch this image and run this service. Hey, I want you to deploy so and so pods on my Kubernetes cluster. Hey, I want you to expose this port to allow users to connect through this port to my Kubernetes cluster. So these are the core programs, and so this with that I guess this is like the absolute basics of Kubernetes. So I'm just going to talk about like what you need to sort of start deploying Kubernetes, or rather a web service on Kubernetes with HTTPS. So basically you need to write an app first. So
Step 3, profit.
Step 1, right? Step 2, Step 3, profit. A quick show, man. How many people here have played containers before? Wow. Anybody else? Interesting. Okay, cool. So we're not that old. I was like, maybe I should learn containers. Never mind, later. I keep doing it, right? Like every year. So at least like the undergrads are still not. I mean, when all the undergrads know containers, then you're like, oh shit, I should learn it.
It's either way too young.
No, I mean, if everybody's using containers, then it means that's the way to do it now.
Some stuff is popular, but it's undergrads will never play.
Yeah, but like, I'm not sure because what happens now is that I was saying that you have a VM. When you see the price charged by Amazon, it makes a lot of money.
Yeah.
Now, like new companies now, they are just like using bare metal for $2 a month.
Which company?
Scaleway, for example. Just Scaleway.
$2.50, right?
Yeah, maybe.
Oh, so you know about it.
Scaleway.
Okay.
Scaleway, maybe more expensive. You have Digital Ocean, but it's like.
Digital Ocean is not bare metal. It's VM.
Yeah.
No, but they are selling. They have bare metal.
They have high compute instances, but they don't say bare metal.
Okay, Scaleway is bare metal.
Is it?
Yeah.
Shit, I should
Scaleway is bare metal.
I'm nothing. I don't write anything that's so computing.
Yeah, and you can rent by the hour. It's just like $1,000 of dollar per hour, or something like that. So it's just like this guy. Yeah, it's just crazy. So you can for $1 you can launch bare metal. You can launch 1,000. So it's just crazy.
Sorry.
So, all right. After you write an app, you are going to sort of like build an image that contains your app. So in this case, right, I have a Node.js app, and so what I'm going to do is I write a Docker file that says that I'm going to pull the latest Node image. Usually, you have some version number here, but I'm just putting latest here. Then my files will have this as sort of like the project root home node. Yes. Sorry. In my image, this will be where my Node.js application will reside. Home node at the app folder within the node user. And I'm going to copy basically. Okay, so right now I'm going to copy my package JSON and my basically my manifest over to over here. Then after I've completed the manifest, I'm going to install the dependencies from here. Then after that, I'm going to copy all my entire program. After I'm going to copy the rest of my program inside. And finally, when I execute this container image, it's going to execute this command. So yarn start, and you'll execute it as the node user. And this is actually not respected by anything, but it's just an annotation to just say that I want my container to serve on 3K, but it's not actually respected by anything. So actually, in this Docker file, I have done a trick here, which is that I copied over my manifest file and installed the dependencies before I copied the rest of my project. So what happens is this: when you build a Docker file, it's going to create a new image, and after each of these commands. All right. Okay. It's going to create a lot of intermediate image. So after it's created this intermediate image, it's going to cache them. It's going to cache them within somewhere. So the trick here is that I copy my program files after I run yarn install, so that when I change my project, this will not run again because it's already cached. All my dependencies are cached. And if you've done Node.js deployments before, you'll know that this can take very long.
Okay.
So
moving on.
So this means that unless I update the timestamp on these files, this yarn install of dependencies will not be executed, and I'll just reuse the old image that already has my dependencies installed. So so this is my Docker file, and to build a Docker image using that file, I run this command. So Docker build an image, and I tag it with this label, and I'm going to build an image with this as my with the current directory as my working directory. So something about Docker is that Docker doesn't play well with permissions. So everything that you run Docker with, you either have to sudo Docker, or you have to you have to grant it like the permissions that you need. But the thing is that allowing the Docker program the permissions that it needs is almost akin to allowing unfettered access to sudo. So it's a matter of picking a poison now. Right. So you build it, and then after that, this command will list like the images that I have. And after that, since I'm doing something open source, I will just choose to push it to a Docker registry, which is just simply Docker push with Docker push my image. If you are developing something in private, you usually will. I think if you log in and you have like some kind of plan with Docker, you can run something similar to this to push to a private registry, or you can like select some other registry that you have with like arguments to this command. So to learn how to like sort of like containerize your application, there's this, you can build a Docker docs, and if you look at the Docker docs, there's like 6 steps, but there's sort of like cheating over here because we only need these two steps to create a Docker image. And since Docker is trying to market its competing solution, it just pretends that they are part of Docker. and so the rest of this are about how to deploy an image. This is using Docker's competing container orchestration service, which is Docker Swarm. Actually, Docker Swarm is easier to get into, but I think if you want to start with some interesting configuration, it gets pretty hard. The documentation isn't that good, and the community also is much smaller than Kubernetes community. So the rest of it is about deploying containers. To create containers, you just need these first 2 steps, and then you can start working with Kubernetes using those containers.
A question. I mean, if you have two containers and Docker,
yeah,
can you put them to top container?
Yes. Usually, you will in your Docker file you'll say that I want to allow my Docker container to sort of like be able to write to so and so folder, or I want to allow my Docker container to communicate on this internet, on this IP port.
Oh,
yeah. So that's how you can communicate with one another.
So you can ask from inside the container of what is your address to.
Yes. Or rather, in Kubernetes, is an internal DNS that you can ping for like what are the services and what where.
Okay. So like this. Yeah. So then in your code, then you have to.
No, actually, to your code, it's just you expose a port, and then that's it. I think that's it. Like if you want to reach out, then yeah, you have to interact with Kubernetes.
Yeah, so you have to inside your own code, you have to write stuff that is related to the container
services, right?
So from within the code, you can write it so that it's like I connect to. Let me check.
I got a response for this. I think it's like if you're writing your app, right, you're listening on a local port. Then in your Kubernetes configuration, you can say that I want this service to serve on all these ports in this local port. So inside, your app just sees like a local port that you can connect to. But outside, you're doing like a whole bunch of shit. Like you're telling Kubernetes like, oh, create this service and like connect it to all these ports with a certain IP address. So inside the local host is 4,000, but outside like some magic is going on. So
yeah, locally you just listen or but you have when you write.
Right, then you have to give, what I do is I give it a configuration file, but then like when you're configuring your pod, you have to attach a volume to it. And then you have to say, I mount this volume on this path. Then I give this path in my configuration file to the app.
Actually,
what I mean is that normally you want to have nothing on your code related to the container.
Correct.
If you start putting something on your code, I mean that then you will. I mean it's
you'll see this configuration later.
Yeah. No, because you just pass it as configuration files, like as variables.
So you define define the ingress and the egress routes in your pods. And then what Kubernetes does is there's this internal system called DGCP, which defines it allows the pods to communicate.
Yeah, but what I mean is that I was asking if it's how easy is the stuff, no? Because this is like
it's hard. It's very easy. It's actually difficult. Like I didn't find Kubernetes easy to use.
No, it's not. I make 2 pull requests for learning it. It's how terrible it is.
But being decorative is
yeah, but because I do that, I mean it's not that easy when you are already on not on the container.
So I think you have to continue.
It's not easy, but it's maintainable.
Alternative is more difficult. That's what they say.
The alternative
is terrible.
Yeah.
It's in the skill for Kubernetes is only apparent when, in my opinion, when you have more like 20 variables.
Actually,
that's when it starts getting unmaintainable.
Where do I find my tab?
Just control page. Actually, just
20, but
it's maybe 3. Just 3. Yeah. Right. You think about it, right? Like, okay, first you deploy your web application in one server, right?
Time I think 20 by yourself.
Okay, actually, let me help you. No, but 3 makes sense.
Oh wait,
example of euros. Look at that.
That's awesome. Shit, that's so cheap.
But it's out of
some. Oh wow, 4 cores.
Yeah, it's not that bad.
I mean the what do you call it? 3 servers are easy. Like when you hit,
you can't count past 3.
No. The reason I say 3 is because like when you are scaling a web service, right? Usually you start out with everything on one server, right? And then the next thing you do is you put the database on a different server, and then you put a load balancer in front of your app server so that you can have many app servers, right?
Yeah.
So like when you reach that point, then okay maybe Kubernetes makes sense, right? Otherwise you have to like manually go and spawn the new server, hook it up to the load balancer, tell the load balancer. I guess.
Maybe when you have thousands and then that's what Kubernetes.
Okay, Johannes, go.
So Kubernetes says that it operates with like both Docker images and what we call Rocket images. But honestly, the Rocket image support is like shit. As in like the documentation is like not there. And Rocket is like this competing container standard. But if you look at the criticism from the Docker CEO, it's like saying the Docker container is already like open source and it's like an open standard already. Why do you want to create another standard?
Because you need sudo.
Yeah, but actually there are reasons for that. But anyway, it's just like not that it's still too immature. So regardless of what you say, don't use Rocket yet. And there's a general container interface being developed for Kubernetes being developed. But the one is still in the future. So yeah, basically support is like don't use it.
That's good to know.
Yeah. So yeah, so you'll see a lot of like marketing for like how to use this with Pocket Sprinkle, not just you don't have to bother about it. So yeah. So deploy to Minikube. There's like this. So Minikube is like basically a local like a Kubernetes cluster. There's like tutorials over here. So this is a tutorial. And as you go through the tutorial, you might need to refer to the API. You like need to refer to the API a lot when you are writing Kubernetes files. And basically these are concepts. What I will do is that after installing Minikube, I launch the cluster with Minikube start, and this command, and so I execute kube control config current context, and this will basically print on like say what sort of like Kubernetes cluster am I like interacting with when I execute a command. If you saw if you like say have like multiple Kubernetes cluster deployments, you'll basically use this to like say which cluster I want to sort of like work with right now. There's a Kubernetes config set context command that allows you to sort of like set which cluster you want to work with right now. So this command does print Minikube if you have only just like run Minikube start, because when you run Minikube start, it will sort of like it will write your authentication. It will write some authentication configuration, authentication and configuration to like some hidden to like your basically your kube control what you call a config directory for your kube control, and so your kube control will automatically like point to the correct Kubernetes cluster, which is Minikube. So this is just to verify that I'm connected to Minikube, and after that I'm just going to launch all my apply all my YAML files. So there are like multiple verbs that you can use. So some tutorials will say you should use kube control create -f blah 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 from this configuration file. But the thing is that with apply file, what you can do is that you can, when you need to modify this resource that you have declared in your file, you can just modify that file and just click apply again. And usually, in most cases, Kubernetes will correctly update the configuration of the resource. But you need to use the apply verb. When you want to create, you don't have to start off. You can also do a kube control get. You can also use the get verb, but it just discourages that. You just say that this is not supported, and then you just do it anyway. But anyway, just use apply. All right. So to have a look at like what these files are like. Let's see. To have a look at what these files are like. This files here. So this is a service file. Every file will have a kind and you have an API version. And basically this is like your you can think of it as like your HTML doc type. It just tells you that it tells you which part of the Kubernetes API you're going to use. So Kubernetes knows that I want to create a service resource and I want to call it write. And this is basically sorry. This is what tells Kubernetes are the Kubernetes pods that will provide this service. So selector at write says that if I have a pod that has this tag at write inside my metadata, that pod is that pod is one of the pods that provides the service. But pod is POD, pod, not port. So when a pod provides a service, it's going to expose a port. And here it says that these ports are going to expose a port, and they are going to provide a service on HTTP over TCP at port 3000. And the type node port is important for Google Cloud Engine if you are going to eventually attach a load balancer to your Kubernetes cluster. So this is like a sample service file. So I have it as one of my repos. And so this is a deployment file which describes how the pods are going to be deployed. So this is a deployment kind, and I'm going to use this API version. So my metadata is, I'm just going to call it right. And this spec selector match tables app right says that this for every service that has a selector app right, I'm going to be a pod that provides such a service. So it's basically going to match all the services that have this annotation, that have this key value config. Replicas tree means that my Kubernetes deployment should attempt to ensure that 3 pods are healthy on 3 pods are provisioned on my Kubernetes cluster. And template basically says everything over here, from here to the end, is basically a template for the pods, for each single pod that is going to be created. So over here, all this data is basic. All this data before the template. All this data before the template basically describes the shape or what kind of deployment that I'm going to have of this pods. And this template over here basically tells what kind of pod I'm going to deploy. So this is all the data that's needed for. So the template contains the data that is needed to correctly configure each single pod. So here you have the metadata labels app right. So I'm just going to use the same name for every single kind. That's right. But if you want, you can just say that like this should be write deployment. This should be like say match tables of write service or something like that. But this would be write pod. But I just for fun just use the same label. Right. But as long as there are different kinds, you can use the same label. So anyway, labels. Every single pod should start off with a write prefix. And this is a specification for each container. The container name the container has a name right. I'm going to pull an image from Docker Hub, and this is a tag that the image has. And exposed to this container are these environment variables, which contains my configuration. So here I will expose a variable named Postgres password. And it's going to be, and the value of this environment variable is obtained from another Kubernetes resource called a secret. And basically, a secret is basically a map from names and keys to like values and files that you just like create. So I'm going to create an environment variable that is going to receive its value from the secret. I'm also going to create this Google client secret, and it's going to receive its value from this secret. So in my case, this was to interface with the Postgres database, and this was to interface with Google OAuth application for sign up and login. And then it's going to, and then I'm going to expose, and then this container will be exposed on the port 3000. So, and with this name as well. All right. So that's it for deployment. And so once you've, and so sorry. And so once you've executed these first two commands, you should have successfully deployed your application onto your Kubernetes cluster, but it's not yet exposed to the outside world. To do this, you should run an ingress. I'll just talk about ingress later, actually much later. And in the context of Google Cloud Engine. So ingress basically exposes a part of your Kubernetes cluster to the outside world. Yeah, but the thing about ingress is that it's a data resource, and the semantics of what goes in an ingress is not standardized across Kubernetes providers. So there's a gotcha that we're going to go into detail later on about ingress. All right. So there it is. Anyway. All right. So something similar happens in Google Cloud if you want to deploy it to Google Cloud Engine. You just can send it to my phone.
Yeah, sure.
All right.
Control Shift N.
This one.
No, just Control Shift N.
Control Shift N. Okay.
He's gonna sign into his Google Cloud.
Yeah. Cool. They can't.
What time does McDonald's close?
11.
It's very good. I came straight for you, dude. Wow.
Okay. And they had no pizza? Are they, yeah?
I didn't go to EF. I've been working from home. Programming. Yeah. So very unproductive to be in the code. You're programming. People are like, hey, can I talk to you?
Yeah, exactly. No, it's good for interacting with people, but not.
Yeah.
Sometimes you need it. Then we are not anymore in a team.
I'm not. They broke us up.
Yeah, this is the point. I don't understand if they broke the team because the team not work or because the project is not working.
What is reason?
It's okay. What is it?
For fun. Okay, so to deploy to Kubernetes, if you haven't used a Google Cloud Service, right, you get $300 free credit.
Yeah.
For that's available for 1 year.
We get 20,000 free credit.
That's been on
USD.
Free.
What?
Yeah.
All right.
This entrepreneurship.
Yeah, because they're like new startup stuff. Yeah.
Wow.
So you just say,
Every individual gets 20,000 free credit.
Wow.
DigitalOcean 10,000.
Wow.
Yeah. Create all the clusters. You get a cluster. You get a cluster. Yeah, my Bitcoin, right?
Yeah,
we should do that.
Actually, I want to burn my credit on Amazon.
Amazon, you have what, 100,000, right?
Yeah.
Oh, yeah. Just do.
I just want
my
to burn
Bitcoin.
put a machine to learn a lot of stuff.
So hungry. Oh no, people are leaving. Johannes, I think you should just jump ahead. No need to demo lah.
Okay. So, all right. So with Google Cloud Engine, right, it's just the same thing. You create a Google Cloud Platform account, put Kubernetes Engine, and just play around with all this stuff. Just configure all this stuff. You probably have to disable as much. Never mind. Because it costs money. So okay, so that's that. Creating. There are like tutorials here as well. Then deployment is similar. So to sort of like tell your kubectl to connect to your Google Cloud Kubernetes cluster, you basically execute something like this command. Gcloud contain. Basically, you download the Google Cloud command line tool, and then can execute something like this command. Actually, Google Cloud Engine is so turnkey that you also have like you also can just like do this. Like if you click this, if you click on the terminal over here, it will just spin up a temporary virtual machine for you to just like run a CLI on. And so when you run this command, it's like mini kubestyle in the sense that you write all the configuration and authentication files necessary for kubectl to communicate with your Kubernetes cluster. And so I just run the same things, and I should have my web service on. Okay, so the thing about ingress is that in Minikube, your ingress represents load balancer implemented using Nginx, and the path semantics of this configuration on Nginx is different from the path config that Google Cloud Engine understands. So, like, say, if I'm not wrong, you can use certain like asterisk to denote like all paths with this prefix should be redirected here, so and so. But with Kubernetes engine, it's different. It supposedly uses like I think what they call like URL APIs or something like that. Basically, it's a Google thing, and so you can see people like raising issues on this on GitHub, like, standardize all document ingress expressions because they're different.
Holy shit.
Yeah.
Okay.
And basically, yeah. So it says, yeah, so and so annotation not supported. Blah 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 blah. So yeah, so apparently GC under the hood is implemented using this URL map. So if you want to configure an ingress on GCE, you should refer to this resource, but it's not really documented anywhere.
What if you install an ingress controller of your own? Can you use the default Nginx like rules and what do you call it?
I'm not sure.
Okay. Shit. No, it's not.
No. I think if I'm not wrong, right?
Okay. Never mind. It's better. We all.
Yeah.
Okay.
I think. No, I think if you want to load balance, you should just use a Google Load Balancer, which.
No way. They say in the documentation it's not production ready and it's not made for load. So
Okay,
then you're like, what the fuck do you call it called load balancer?
Alright. Anyway, yeah, that's it. Set up ingress, then set up DNS. Basically point to your basically from here you look at your IP. There's some section over here that lists all your IP.
It's up there. It's up there. Bookmark it already. It's up all the way up. PPC network, I think. Yeah. External IP
addresses.
Stupid JavaScript. Excuse me? No, it's really stupid. The UI, not JavaScript, the UI.
So every node that you spin up on Google Cloud Engine is going to be assigned an IP address, but these IP addresses are subject to be changed. And if you want to fix an IP address, you have to pay money for it by making static. So basically here
it's free if you attach the resource.
Okay.
You can see that I read the documentations too much. Go on.
I think only for your first one, right?
What? I spin up a test cluster, then I
like you get like files. Yeah,
Is it? Oh, okay.
Yeah, in Scaleway, it's interesting because you can buy separately the IP address. So that means that you can have everything that is on the back end don't have duplicate cables. So you have like yeah.
So so basically when you create an ingress resource, it's going to be associated with an IP address. You want to make the IP address static. So here you can see that it's associated with my load balancer ingress. So after you have this IP address, you can just configure your name server to configure. So that's setting up DNS. All right. So another thing that you're probably want to configure is like configure Helm. So since we are just doing this for fun, and it's not really like critical to anything, we can just misconfigure it. So there's this documentation, and the Helm website is very good. It has all these like newfangled scrolls that make it very hard to scroll. But anyway, that's a tutorial.
Next.
Sorry.
Just say what is Helm, then next.
All right. So what's pertinent is that with the recent Kubernetes versions, there's going to be permissions, and Helm basically is like pip or apt-get or what do you call it, or npm, in that it sort of like gives like a turnkey solution for deploying an app. So basically you just type Helm space install space so and so like say Rails server in a PostgreSQL server, then you'll just install a PostgreSQL service and pods into your Kubernetes cluster. But to do that, it has to have like some sort of like manager program for it. And the problem is that with the permissions system introduced in the latest Kubernetes version, the default like Helm init, it can't sort of like does all this stuff that it needs to do. It needs like basically a lot of permissions to cluster-wide permissions to do it, or at least like permissions within your namespace. So you can what you do is that so what you do is that you create a file of cluster role binding that binds this user called Kube system to have like pseudo permissions within our cluster. By default, it can only access its like administration namespace called Kube system. Basically by provisioning this resource, you are telling the Kubernetes cluster to give it like all the permissions to access every namespace in the cluster. So after you do that, you can do Helm init and you install that service called manager is called Tiller, Tiller, and after that, after you do Helm init and install it to your cluster, you update your list of available Kubernetes applications by this command Helm repo update, and then you can just like install a new service and pods and deployment just by this command Helm install blah blah blah. Of course, usually you have to eventually like look at the documentation on what this stuff says on this application to see how to configure it to interact with your application. But it's just like but Helm is good for like stuff like monitoring programs and reporting the health of your cluster. Because like these applications are like pretty standard across every cluster, and you want to install them quickly and like with as little configuration as possible. All right, so after we've installed Helm, we'll basically try to install HTTPS, which is like a huge pain. I'm going to install an application that basically supports the ACME protocol to get Let's Encrypt to give me a certificate, a certificate that I can use to serve HTTPS. To do this, right? In this case, in my solution, I've chosen to sort of like authenticate with Let's Encrypt using what it calls a DNS challenge. So what a DNS challenge in this case means is that my server, my application will call it Let's Encrypt server, and the Let's Encrypt server will say that hey, if you to prove that you own so and so website, you should change the DNS record of their website to include this string. So in this case, right, since I'm configuring my DNS, my Kubernetes cluster needs to be able to access this DNS provider. So in this case, I'm just to make it easy. I don't know if it's to make it easier or to make it possible, but in order to do that, I choose to serve my DNS using Google Cloud Engine, and
another.
sorry,
I think it's download
it's
services.
registering.
Download services. Down. Two rows. Download services.
Yep.
Yeah.
Yeah. Oops. So I'm serving it via Cloud DNS. So these are my DNS records.
You
All
have
right.
to pay for this too.
Oh yeah, yes, I think for this. Right. And to allow your compute to access this,
$2
you use a service account.
$10 for the IP address.
So I create a service account and say that I give it modify permissions. Then associated with this service account is an authentication token, and basically I include the authentication token as a resource in the application. So how do I so what application is it that I'm actually using? I'm using this.
Look at that. That's me.
Really?
The latest
using
commit is me. Yeah.
Oh,
Because they fucking didn't include or update the one library.
right.
So
At least it got
painful.
merged.
What?
At least it got merged.
It did. She was actually pretty responsive.
All right, so basically I'm using this, but if you look on Docker Hub, does it have an updated image?
No, you have to
No,
serve
right.
your own.
Yeah, so basically I look at the issues again, and there was some guy pointing me to the 0.5.0 version. So I got that version and I just uploaded my own copy of it so that like nobody else can take it down.
Yeah.
Right. So yeah, very like a lot of watch charts here and there.
Yeah.
Yeah.
I don't even know why I bothered.
All right.
Yeah.
So so I also have like a sample deployment on GitHub.
Enough. Just go.
And basically, the idea is that we create a certificate over here, a certificate resource over here, and then so your Kubectl manager will request and create certificate resources within your Kubernetes cluster. So what's going to happen is that I create a service. Sorry. Yes, to have this service account to interface interface with to be able to manage the certificates within the account, within the Kubernetes cluster. And in addition to that, basically this is to give it permissions to access to create resources within a cluster. Then it needs a provision storage volume to store the certificates and its data. And this is a deployment. So spec strategy, we create these pods when they die. I've created my own tag for this image because it really was difficult to find. Then arguments, data directory will be exposed to a container at this path. The URL to connect to authenticate with ACME is over here, and other metadata. And so these two variables, GC project and Google application credentials, basically say that I want to use these credentials to be able to access the DNS configuration from within this container. So that's why I pass the credentials here. Then, as usual, and this is to configure mounting storage volumes onto this pod. So this is the volume mount. This specifies what path the container will see it as, and the volumes here say which are the resources that I want to expose to containers. So this one is the API to the Kubernetes cluster. This specifies an API to the container within. And so this account keeps a manager so that I can have the permissions to create the certificate resource. So this is a deployment. Then it's going to be exposed as this service over here, which is pretty short. Exposed as 8080.
Johannes, I think we don't have time to go through everything line by line.
All right. Okay. I'll be done soon. And finally, provision a certificate. And this certificate provisioning is necessary, even though the documents say that it's not necessary. And so once I'm done, I'm able to configure my ingress to expose a HTTPS connection, which is keep that. Which is over here. Ingress. So these annotations will, okay, so this first annotation says that it's going to be exposed at this static IP. And the rest, actually, it's an error. But anyway, I think there's an annotation that says that I'm going to configure it as TCP. But it says, well, anyway, backend says that this ingress will redirect to this service. And it's going to be exposed at this URL, and it's the URL should have this basically every single location starting from this URL. And it's going to be, and so this is and so basically every access to every attempt to connect to the Kubernetes cluster with this URL will be redirected to that service. And this URL and this URL, and I'm also going to have rapid and HTTPS for these two hosts as well. So that's the ingress, and that's done now. So it's being served on a Kubernetes cluster, which is just a stupid, like this is a root route page. Underwhelming, right?
A lot of work.
Yeah, so
Well, at least now you can scale through.
That's it. Yeah. All right. We're done.
Yeah, that was, yeah.
Okay,
thank you.
I think billions too low. It's just one. It's not even HTTP.
Is it-
just string.
Is there a challenge to DDoS?